Hello and welcome to Learn from a Layman. I am Carl Christensen, and as always, I'm back with Cameron Christensen, Matt Christensen, and Timothy Cox. The end. Yeah, I don't like the music, so pipe down. Today, we're going to be tackling the thrilling, gripping, and sometimes nightmarish subject, calculus. So, I believe that I took this in high school, though that might also have been a very bad dream. I don't remember significant portions of that year, so I'm going to let Matt take the bull by the horns here and walk us through a little bit of the basics of calculus. We'll discuss what we need to know and why we need to know it. Matt?
Okay. So with that, almost everybody has heard of calculus. Not a lot of people have actually taken it or know what it is or how it's useful. And to some degree, that includes myself. I've taken this thing, but the uses of it are often very specific unless you're in some of the hard sciences or research fields. So with that, I will try to do what I can with an overview here. Calculus is basically the study of how mathematical functions change. And there's really two parts to it. There is differential calculus, or derivative calculus, which deals with the rate of change of a thing. And then there is integral calculus, which deals with accumulations of volume or area or product or something as a result of a function. And so, yeah, we can just jump right into this if you like.
Sure. So you just said there's kind of these two different parts of calculus. If you take a basic calculus course, as some of our listeners might have done, do you get both parts, or is usually one of these covered more in your high school or early college level basic calculus courses, or are they both just kind of given cursory treatment, and then for example, in classes that you may have taken in college, are there different specific differential calculus courses, or are they always handled as one unit of just one calculus curriculum?
Well, yeah, when I took calculus, it was essentially the intro to calculus dealt with differential or derivatives, and then calculus 2 or calculus BC, they called it, dealt more with integrals. And then you can sometimes have calculus 3, or sometimes it'll be called something else, but that starts to deal with multivariable calculus. And
let's not go there.
Well, weirdly, multivariable calculus was the one that made the most sense to me. But
it's unfortunate.
I know it was. But that's okay. So yeah, we're not going to go into formulas, and realizing that this podcasting format, there's only so much that we can really attempt to present in terms of the information. We don't have chalkboards, PowerPoints, or anything else. All you have is the soothing sound of my voice and the occasional background noise.
Are you talking about Tim?
No.
Oh.
But anyway.
Okay.
But we will try to, I will attempt to describe these concepts, and yeah, let's launch into this thing. So anyway, calculus. Calculus was, again, calculus is dealing with a mathematical function. And when we say function, we're talking about an equation that relates one or more variables to another variable. The classical functions are x and y functions. If you imagine an xy grid or graph, you can have an equation that shows how x changes as y changes. The very basic function is x equals y. So when x is 1, y is 1. And when x is 2, y is 2. And if you graph that on a piece of graph paper, it's a straight line at a 45-degree angle going from the bottom left to the upper right. And that's it. That's a very, very basic function. Calculus deals with change in the lines that are represented by those functions, and it also deals with the area under that line. The change is the derivative part, and the area under the line is the integral part. The basic function that I'll want you to visualize is, imagine you have a field artillery piece, because most of us have one of those in our backyard. You crank the barrel up to about 85 degrees, so it's pretty steep. It's not vertical, but it's pretty steeply inclined. And you fire it as you do. The shell goes way, way up, and at about however many thousand feet, it levels off. It's moving away from you horizontally, and then it comes right back down and obliterates your neighbor's house a few blocks over. The arc of that cannon shot can be considered a mathematical function, and that the shape of that arc, that really tall parabola, is what we'll be talking about. So imagine you have that parabolic arc as represented by that cannon shot. Now, at any given time, because you've suddenly become fixated on understanding everything about where this shell is throughout every moment of its flight, at any given time, you can determine the position of that shell using an equation that relates its x and y coordinates. For instance, if the parabolic equation is a y equals x squared kind of function, you know that when x is 1, well, 1 squared is 1, so y is 1. When x is 2, 2 squared is 4, so y is going to be 4, and you can see that line is going to go up pretty steeply. Now go back to that cannon shot parabola. That's a mathematical function of some sort, and that function will tell you the position of your shell based on those x and y coordinates. But what if instead of the position of that shell, I want to know the direction the shell is headed at a given moment? The instant I fire my artillery piece, I know that that shell is headed out of my gun barrel at 85 degrees, right? Because that's where my gun barrel is. Yes? Somebody acknowledge.
I think that is the case.
Yes, it totally is. Okay. The instant after the shell leaves the barrel, it starts to, its trajectory alters, and its line of ascent changes. And at the top of that parabolic arc, what way is the shell pointing? It's pointing flat horizontal, isn't it? As it's right about to come back down. So throughout the flight of my little shell, I've gone from an angle of 85 degrees to an angle of 0 degrees. And now I'm going to start plummeting back towards Earth, and my angle is going to drop. If I want to understand that change in the way that my shell is pointing, that's where a derivative in calculus can come in handy. Your derivative of a mathematical function is going to give you the slope of your line at any given point. If I take the derivative of my cannon shot parabola at the top of the arc, it's going to give me a slope of 0. That's the point where the cannon shell is at the top of its arc, has leveled off, and is just about to come down to Earth. If I take the derivative of that function at the initial point, at time equals 0, I'm going to get a slope that will be equivalent to my 85-degree elevation for my gun barrel. And if I take the derivative of that function at the impact point, I'll similarly get a negative 85-degree slope. And that is what it is. That's the kind of first application of calculus here. if you want to know the slope of a line at any given point for a mathematical function, you take its derivative. And the rules for that you can find in any calculus textbook. You can look them up and play with that all day long. I don't care. But that's more or less what, this is the basic concept of what you are doing.
And that also helps, and the reason, well, among the reasons that would be useful for the layman, would be so you can know how far. So if you can know the slope at any given point, you can also then calculate the distance that the thing's going to travel before you shoot it, right?
No, not almost. And we're going to get a little bit confusing here. The initial function, that parabola that you trace out, that initial mathematical function will define that parabola, and that will tell you position throughout the entire flight, and that tells you the endpoint and everything else. What it doesn't tell you is the slope of the parabola at every point. And so I'm going to shift gears here and use a different example. Another function we're going to use is the position of a car. Imagine that you are in your car, you are stopped on the street, and you start driving forward by pressing the accelerator. Now, what is your speed? It's changing. You do not go from 0 to 60 miles an hour instantaneously. You go from 0 to 1 mile an hour to 10 miles an hour to 45 to 120. And you do it over time. The other part of this is consider how you apply the accelerator. When you are at a stop and the light turns green, do you stomp the pedal to its maximally depressed position and just flood your engine with gas and blast yourself off the line like the boss that you are? Because that's what I do, but most people don't. Or do you gradually ease into it by depressing your accelerator a little bit and then a little more until you get up to speed, and then you kind of open it up and really start moving forward?
Depends on the day, but I generally go with the second one.
Yeah, most people do, because most people are actually fairly reasonable drivers. But the thing is, when you do that, you're pressing your accelerator down to a varying degree. That also means that your acceleration is not the same as you speed up. And so if you want to trace the position of your car, you have to understand that you're not dealing with a constant speed, and you're not even dealing with a constant acceleration. And if I really want to model the entire dynamics of my car moving forward, I need to know those things. Fortunately, I have calculus. If I can define a function that determines where my car is over time, then I can take the derivative of that function to determine its speed at a given instant. And with that, I can take the second derivative. I can take the derivative of that same function again and determine the acceleration of my car at a given moment. So let's say that I accelerate from 0 to 50 miles an hour, and I do that in so many seconds. I can, if I've got the positioning of my car and I've got the function that represents that positioning as I'm zipping down the street, I can use the derivative of that function to pull out my speed at any given moment, all the way from when I started at 0 to when I hit my steady state at 50 miles an hour. I can then take the derivative of that derivative and get my acceleration all the way from when I was at 0 to when I started to press the gas pedal and I was accelerating slowly, to when I stomped the gas pedal and I was accelerating quickly, to when I let off the gas pedal again and my acceleration dropped to 0 and my speed remained constant at 50 miles an hour. That is the type of thing that differential calculus allows you to do. Take a position function, take the first derivative of it to get your speed at any point there, and take the second derivative of it to get your acceleration at any point. that has a number of different applications depending on what it is that you're trying to understand and model. Going back to my cannon shot, the position of that shell in three-dimensional space, or rather in two-dimensional XY space, is represented by some function. I can determine the angle it's pointing by taking the slope of that line at any given point by taking the first derivative of that function. That's kind of some two basic examples of what you can do by taking derivative functions of a or derivatives of a standard position function. Any questions on that?
Yeah, so that for the first analogy we're making with the bullet that you shot.
Yes.
So once again, for the layman, if I want to know the distance of the bullet when I shoot, before I shoot the gun, if I know the rate at which it accelerates and the angle at which I'm shooting it, and I can plug those into these derivative formulas, and then that will give me the endpoint.
Ho ho, you would think that, but you'd be wrong because you're going the wrong way. If I know the acceleration, then I need to determine my position function, right?
Yeah.
And to do that, I have to go the other way. I'm not taking derivatives. Now I have to go backwards, and that means taking integrals. So let's say that I know, for example, we'll shift to the car analogy because this is a little bit easier. Let's say I only know how hard I'm going to stomp the accelerator. And I know how hard I'm going to stomp the accelerator at every moment throughout my car's little journey. Can I figure out how fast I will be going at any given point? And with that, can I figure out my position at any given instant? The answer is yes, I can. But now I'm not taking derivatives because I'm starting with a derivative. I'm starting with a second derivative. I'm starting with acceleration, and I want velocity and position. And the way that I get that is with the second half of calculus, which is the integral side. And we can jump right into that unless you've got any other questions about derivatives.
I don't think so. So I mean, so derivative. Once again, I'm trying to make this as layman as possible, and it should be easy because
as long as I understand, I'm probably failing, but oh well.
Well, no, I'm just trying to put it in terms that I understand, given that my calculus exposure has been minimal, and Cameron and Tim can also chime in if they so choose. The derivative is essentially just finding out the slope, right? It's just a particular variable. It's like,
in general, it's rate of change. When you look at the rate, when you look at the rate of change of position, that gives you velocity. When you look at the rate of change of a line on a graph, that gives you slope. And when you look at the rate of change of velocity, that gives you acceleration.
Right. And so, yeah, Cameron?
Oh, are we assuming this is all done in a vacuum or actually on Earth? Because that would change your.
No, it doesn't.
It doesn't? Wouldn't the rotation of the Earth also change your trajectory?
No, it depends on how accurately your function that defines the flight path of your bullet is, or how accurate the function is that defines the way that your car travels. If it accounts for all of those different factors like air resistance, the Coriolis effect, whatever else, great, that's fine. But at the end of the day, no matter how precise your function is, the way that you back out velocity from position is by taking the derivative, and the way that you back out acceleration from velocity is by taking another derivative. The way that if I have a function that gives me an approximation of the trajectory of my little bullet, then by taking the derivative, I will get an approximation of the angle of that bullet at a given moment. If I have a function that precisely models down to the atomic level all of the interactions that explicitly define that bullet's flight path, I would do the same calculus equation on that function, and I get a very, very precise equation, that a derivative that shows me that bullet's pointing. Does that make sense?
It does.
Okay.
Sorry, one other thing really quick to make this also more, right now, so those, you're just mentioning the word model in our current
I'm thinking
climate.
Specifically of Kate Moss.
Not that type of model.
How do you know?
No, predictive models, right? So calculus, these types of models can be used in prediction. I
think Kate Moss is a Libra.
Oh my
gosh.
Yeah.
But never mind.
We're not going down that road. No, the idea of predictive models and computer modeling, and so that's my limited exposure to whatever calculus I actually have used is in computer modeling. So we're talking about cars and bullets, and because those are things that everyone has kind of real world familiarity with. But when you see a model in, for example, modeling the coronavirus, they have models that have been trained on data. So essentially they're trying to create functions that are going to predict this curve. So they're going to predict, so they're doing that using a calculus type function, or differential/integral function, right?
Yeah, the coronavirus is actually a really good kind of way to illustrate some of this. So imagine the graphs that we've all seen showing the number of new cases every day. If I know the number of new cases every day, and I know the total number of days, I should be able to figure out how many total people are sick, right? Yes, you totally can. Yeah. And that goes kind of into that second branch of calculus, the integral calculus. Integral calculus can be thought of as defining the area underneath a curve. So going back to my artillery shell carves out a beautiful arc in the sky. How much two-dimensional space is underneath that arc? Well, if I really wanted to find that out, I would take the integral of my bullet function, and it would show me that there are X many square feet of air underneath my arc. Likewise, if I have a function that tells me how many cases of coronavirus I'm getting every day, how many new cases, and I can determine the equation for that function, then I can take the integral of that function, determine the area under the curve, and that is my total number of sick people. It also goes back to your question about the acceleration of your car. I have a function that tells me precisely how my car is going to accelerate based on how I depress the gas pedal. If I have that, then I can take the integral of that function and I can get velocity or my speed. And now I've got a function that determines precisely how my car's speed or what my car's speed is at any given moment in time. Well, that's neat, but I want to know my position. So if I take the integral of my speed function, I can now get my position out of that. This kind of goes to the fundamental theorems of calculus, and well, I don't actually want to touch on that, but the basic thing is, if you have position, you can take the derivative and get speed or velocity. If you have velocity, you can take the derivative and get acceleration. If you have acceleration, you can take the integral and get velocity. And if you have velocity, you can take the integral and get position. So if I have any one of those three functions, if I have a function that gives me my position, or my function that gives me velocity, or my function that gives me acceleration, if I can do calculus on that one thing, then I can determine the other two things out of it. Give me velocity, and I can tell you position and acceleration. Give me acceleration, and I can tell you position and velocity. And it's just a matter of taking the appropriate integrals or the appropriate derivatives to find the missing functions. Does that make sense?
Yes.
I think so. Though I do... Sorry, go ahead, Cameron.
No, I was going to say, I had to do that for a college class in my, what was it? Biomechanics class. So you had to do stuff like that all the time.
Yeah. So if I had a function that told me the total number of coronaviruses every single day, I could take a derivative and I could tell you the change in coronaviruses every day. That's my new cases. And then I could also take the derivative of that and I could tell you whether the change is increasing or decreasing every single day. And you look at that and you think, well, duh, I can look at that by reading a graph. Well, yes, but you can define it precisely with your derivative and your integral functions. And using that, you can respond to it more precisely as well.
Right, and that's what gives once you have the formulas and the functions, that's what gives you the predictive power.
Yes,
the idea,
exactly.
Right? Because then you know what the curve looks like, you know what's going to happen, at least ideally what will happen in the future.
Yeah. So if we can get the coronavirus to the point where the total number of cases is increasing, but it is increasing at a slower rate than it was yesterday, that's a good thing, because my derivative will show me that my new cases per day is less than it was yesterday. And my derivative of that would show me that I am actually seeing a negative change in new cases. And the amount of that negative change, how steeply that line is headed, will determine my public policy, if I'm a responsible person, on how much I open up, how much I stay inside, how long I think we're going to have to weather this, how much toilet paper I hoard in my house. All of these types of things give you that predictive power based on the slope, the change in those lines.
Now, another question. I don't know whether or not. So you mentioned right off the bat multivariate calculus. In a scenario like this, or any type of modeling scenario, and where Cameron kind of already mentioned before with the idea that if I'm shooting a bullet, the questions, I mean, obviously you have speed, you have acceleration, you have angle, but then with the coronavirus, you have lots of other factors, other variables that could potentially be taken into consideration in the models to better be able to predict, right, and better to be able to fit the line and be able to. So is that multivariate calculus, the idea of taking in other variables and being able to use them also in determining these functions?
Yes, kind of. It depends. Okay. I'll make a distinction. There's a difference between a variable and a factor. So the rotation of the Earth. The rotation of the Earth is fairly constant. The Earth rotates. That doesn't really change. But if I am faced with a factor that changes at the same time that my other factors change. So I want to know my coronavirus infection rate, right? Well, another factor that might change alongside that is the number of people that I have wandering around outside based on my lockdown measures. Right. That is a variable that is going to change over time at the same time that my coronavirus infection rate is changing, and they are going to influence each other.
Right.
And so that's where multivariable calculus really comes into play. I have two things that are related, that are part of that same function, that change in different ways and influence my totals. At that point, my math gets, well, there becomes more math. And right. We don't want to go into that because I don't want to.
Right, but yeah,
but the
so I guess
fundamental
my point...
principles are, yes, you're still taking derivatives and integrals. There's just more.
Right, exactly. So I guess my point was like, you see lots of models out there, and you might wondering how they're modeling and what exactly they're taking into consideration in their models, but that is actually where you're getting the huge difference in these predictions, is what they are taking into consideration. The variables that they are using to define their functions has a huge bearing on what the predictive value is going down the road, because obviously, as you can imagine, if you are not taking into consideration well, like Matt said, the number of people outside in a model where you're trying to predict who gets sick, that's not your curve is not going to be particularly useful, other than fitting the data that you already have, because its predictive value after that is not accounting for a variable that influences the curve.
Yeah. So here's the thing. You remember all of the story problems that we had to do in our math classes that we hated so much?
Yes.
Yeah. Well, it turns out those are the only ones that actually matter in the world, because actual mathematical equations are super easy, to the point where you don't have to think anymore. We have computers to do that for us. And you chuck your equation into a calculator and it spits out an answer that will be correct. That doesn't mean it will be accurate, because even before you calculate something, you have to have set up the problem correctly. All of those story problems were trying to teach us how to set up equations, and the correctness with which you set up equations determines the usefulness of your answer. So if I've got some guy at the CDC who is chugging away at an equation, and I generally have faith in the CDC. Hopefully he's got good info and is accounting for the right variables. He's going to come up with an answer. Now, if I have some idiot on some ultra right-wing or ultra left-wing political blog who is chugging away at his own equations because he thinks he knows better, and he comes up with a different answer and starts blabbing that to the world about why we do or don't need to freak out a whole lot more, my big question is going to be, how did you set up your data, you moron? And I will make sure that I put that part in there as well. Because, just because some guy comes around waving math at you doesn't mean it was done correctly.
Right.
And the alarming thing is that when you get people that do know this stuff and they still come up with different answers, because, there is uncertainty and we miss things and we're dealing with things that are new. One of the great things that you hear in the scientific and mathematical communities, whenever we're talking about new discoveries or new ideas and new equations and stuff, is the term peer review, which means that you throw out your work out to the entire community and say, hey guys, I think this. Is that right? And you have to have your peers look at it, because supposedly you're a top of the line dude in your field, and you need all of the rest of those top of the line men and women to look at your work and not check the arithmetic, but to check that you actually set it up correctly. So anyway.
Yeah, for sure.
Isn't this where most people hate outliers, because it totally screws up your pretty equation?
Oh, yeah. And statistics is a whole nother fun field to talk about at some point.
Well, I can pose this as an example. So we had two businesses in our community that decided not to follow safe practices with the COVID, and now entire sections relating to certain zip codes, all residents are now required to be corona tested for that. So things like that can obviously screw up data points, correct? Because you have a model, but then you get people that do things like that can screw up your model.
Yeah, that's a good point. And anytime you try to model human behavior, you're going to have outliers and issues. And there are ways to account for that tune in next time when we discuss standard deviation and statistics. But yeah, it all comes down to functions that represent the real world and how closely you are able to get them to do that, accounting for the outliers, accounting for the predictions, accounting for everything else. Can you get your function to represent something correctly? And then regardless, if you have a function, can you figure out the calculus used to draw the conclusions that you want from it? My rates of infection, my velocity as I'm cruising down the road, my position in the air, my pointing direction, the appropriate altitude at which I need to set my fuse to detonate. Well, maybe not that one. Anyway, calculus is something that is used in dealing with all of these types of things. So,
yeah, I think once
How
again, before
fast does Johnny need to run when he lights his firecracker so it doesn't blow up in his hand or something like that?
yes.
So yeah, I like you said, getting now back more towards integrals. If we want to revisit that, I don't know if you got that too far there, but generally, it's useful to know these real world scenarios, so that, like you said, you know how and what tools, what mathematical tools are available to you in order to try to solve an issue. So knowing that you have to take into consideration these things, that derivative calculus will help you determine a particular slope or whatever change, the differential equations versus integrals, the numbers under the line. So, but knowing the tools that's essentially tools in your toolbox in order to be able to solve real world issues. But the real world issues are messy, but without the tools in the toolbox, namely calculus or other, mathematical or statistical functions, you're not going to be able to solve these issues as well.
I think that was a beautifully succinct summation of everything.
Good.
And that's really all I've got on this intro to calculus.
Nice.
There are two parts. Derivatives deal with rates of change, and integrals deal with areas under the curve. They have applications all over the place.
So we should be asking when we disagree with things, what did you use as your model? Not,
right.
Not I disagree with what you're saying, just what are you using?
Yeah.
I think that's a good thing to kind of get out there.
Yeah, absolutely. When you see scientists coming together in disagreement on something, the disagreement never centers around their math. The disagreement is always about their assumptions or the way that they set up the equation. Nobody ever talks about, hey, you added this one wrong.
That's because 2 + 2 is always 4, right?
Yeah, exactly. And the integral and the derivative of a given function is always going to be whatever it is, and you can figure it out with a computer. As you said, it all comes down to, did you set up the function correctly? Did you account for this variable or that variable? Did you account for the idiot who's outside protesting and breathing on everyone because America? All of that kind of stuff.
Yeah, so I think this is, once again, if there are students or people that are potentially interested in learning calculus, this should give you some motivation. So you can't really engage to the same degree in without having the tools to be able to intelligently engage. So understanding derivatives, understanding multivariate calculus, which I don't, but which is why I don't engage with these scientists that do as much, besides just trying to generally be informed as to what type of information they're using. But just have that in your toolbox, be aware of it, and it's then all of a sudden calculus, well, it's not going to change your world, it'll all of a sudden help you understand the world a little bit better. So Tim, I think you should have the final word on calculus.
Well, I'll just say it gets used everywhere. We even use it in schools. Calculus is used every year to pass certain kinds of AP tests. So
is it calculus test, you think?
Yeah. That's
interesting.
What I think Tim meant to say is that we can use calculus to predict the passing rate of the students in the school system.
That's right. If we know the rate at which students are taking the class, and
exactly.
Well, you can calculate their grades, their how well they pay attention to their homework, stuff like that. I'm sure you could use those variables to predict a score.
Very complex math.
So one last just word of advice is at least something from my limited exposure, once again, to calculus. It's very easy to glaze over when you hear either the word derivative or integral, or you see those mathematical functions with Greek characters in them. Take it piece for piece. Like I said, try to understand individual terms and words before you try to, you can't eat a elephant in one bite. So if you break off little pieces, for example, learning it from a layman, and just try to understand what a derivative is and how that might be useful, like we just talked about, and then go from there. Like I said, there's a lot more in calculus we have not gone through that Matt didn't walk us through today that maybe we will in the future. So if you'd like to hear more about calculus, let us know, and we will be back again next episode with more informative tools that you can use in not being an idiot.